So now we're going to see the force method in this video. Force method. So in this force method approach, what we are going to assume is that the force, reaction force at Bx, we are going to make redundant, right? So this Bx force, this Bx part, we are going to, so this part we are assuming that it's not a fixed support, and we will apply the external force instead of fixed support here as a reaction. So that is what we are going to do in a making redundant reaction Bx, right? So we are going to make Bx force redundant. Okay, so if we are making the Bx force redundant, so there will be three forces acting on it. First is the pressure loading because of 49,000 and minus 20,000, right? And it will, let's say it is giving a rise to deformation of delta at delta B end of delta B P. P indicates pressure load. Then first we'll consider pressure loads, then we'll consider second effect in force method because of thermal load, right? So we are applying a thermal load of delta T equals to 60 degrees Celsius. So because of its heating, it's going to expand. So let's assume that this B end, because of thermal load, is expanded by amount of delta BT. Then as we have made the B support redundant, we are going to assume that there is external force at this point. So we are going to assume there is an external load acting Bx here, and which is giving a rise to delta B because of external force. So basically there are three forces: pressure load, thermal load, and external load because of reaction, right? We are redundant, or we are eliminating this B end force. So delta B, the total deformation will be delta BP plus delta BT because thermal load, and delta B external because of the reaction load, right? So there will be total deformation of B end, this much. Then we are going to find out each loads. First let's do according to pressure loading. Because of pressure loading, let's find out the internal forces in each member, because you know that the deformation due to pressure loading can be given by like this: P1 L1 upon A1 E1, right? Deformation due to PL upon A, plus P2 L2 upon A2 A2 plus P3 L3 upon A3 A3. We know area, Young's modulus, and length. We are not knowing internal forces. So how to find out the internal forces? So we are going to divide this into three sections. Let this be the section 1, let this be the section 2, and let this be the section 3. Pardon my chicken scratches. So at section 1, the force, internal force because of this will be equals to 0. So right hand side of this 1 number point, right, P1 equals to 0, P2 right hand side it's minus 20,000 at second point, and at third point we have minus 20,000 and plus 49,000, that's 29,000. So P1 is 0, P2 is minus 20,000 and P3 is 29,000. We know that length, area and Young's modulus value. So if we put this, all the things in above this equation, we will get this delta BP equals to 0.0182 mm. So that's deformation due to pressure loading. Similarly, we are going to find out for thermal loading. So this is subjected to temperature rise of 60 degrees Celsius, right? It's rise load. So here, because of thermal load, we are going to get the deformation at this point of delta BT amount, and that can be given by this, right? So alpha L delta T. We have seen this equation already in the very first video of this second lab. So delta BT is equal to alpha 1 L1 into delta T. Delta T is 60 degrees. So if we'll put L1, A1, E1 and alpha values and delta T values, we get the deformation due to thermal load as 0.2544 mm. So we have done pressure loading, thermal loading. Now let's do for the reaction loading. Now at this end, we are assuming that we are eliminating the fixed support and we are applying the reaction force as external load, right? So let's assume right now it as positive Bx load applied here, and that is resulting in a deformation of delta B external. So there will be three sections, as you already know that. This section number 1, this is section 2, and this is section 3. If we do the deformation due to reaction end, it will be Bx L1, because there is only one force, there is no forces at any other point, right? So there is only one external force we are assuming right now. So Bx into L1 upon A1 E1, Bx into L2 upon A2 A3, Bx into L3 upon A3 E3. Right, so here we have came to the point that let's take Bx common, and these things, let me write this parameters as multiplication factor. Let me write these things as a multiplication factor. So I can write down multiplication factor as L1 upon A1 E1 plus L2 upon A2 E2 plus L3 upon A3 E3. And so delta BR will be Bx into multiplication factor. I know the multiplication value because I know L1, A1 and E1 value. So if I'll put this L1, A1, E1 values, I can get the multiplication factor as 4.7429 into 10 to the power minus 6 mm per Newton. Right, so we get delta BR equals to Bx into this value, which is 4.7429 into 10 to the power minus 6. Right, so if we'll, so here unknown is this Bx. So if we'll put this and combine this in the equation which we have written here, very first equation, this equation, delta Bp plus delta dt plus delta B external is equal to delta B. So let me write down that equation. So delta B equals to delta B pressure plus delta B temperature plus delta B external load. So this, let's assume that is balanced, this equals to this, so equals to 0, right, because there is no deformation at point B. Point B is fixed end, right? So this point is fixed end, so delta B is equals to 0. So delta BP plus delta BT plus BX into 4.74 into 10 to the power minus 6 will give me the BX as this, 49,803.21 Newton. And AX, from first our equilibrium equation, we can get AX equals to BX plus P3, which is equals to minus 20,803 Newton. So we got the reaction forces at B end and at A end. Now let's see the stresses. So stresses is very simple, is equal to force per unit area. So these are the forces. At right hand side of this first point is only Bx, right hand side of second point is this Bx and minus 22,000, which is coming to minus 69,000. At right hand side of P3 it is minus 20,000. So that what is being also cross verified with this. So equilibrium is achieved. Stress is equal to force per unit area. So stress in first component we can get by this, force 1 upon area 1 as 166, 139 and minus 20 megapascal. Now let's see this and compare with the ANSYS results also. So in ANSYS we get internal force minus 20,000, here also minus 20,803, minus 69,803, minus 69,803, minus 49,803, here also minus 49,803. Let's see the stresses value. In first section it is 166.01, it's 166.01, exactly matching. Then 139.61, 139.6061 and minus 20.803, exactly matching sigma 3 value. So this way we can compare the hand calculation value. Also you can see the deformation at point number 2 by using hand calculation. So that's all in this lab 2. Do the exercise, do the practice, and then submit the assignment question and get the credit. Thanks.